Okay, drinking time first. 腹部鱼到家起，推家远坐，路一展，摇如歌，李宗浩 ，Risky， 整拿，丁，春拿。蔡家峰 ，Luxy， Okay. Before the festival, we introduced the analysis on the antenna arrays. And the first we set a uniform distribution, right? And both have the same, all of the elements have the same phase vector and also the same amplitude. And for that, if we have, for example, 7 elements. For an example, and so the distributed the pattern distribution, it looks like it has a main lobe, right, and several side lobes. Okay. Like that, not exactly, but yeah, just an approximation. And here we set the distribution for each neighboring elements should be d, all right, the distance. So d, we set d equals half of lambda, all right. So and when we increase the separation to, for example, d equals 3 lambda, and we get the main lobe narrower, and also have several side lobes. And also we have another like this one, and then smaller ones, all right? This one. So this one is the main lobe, right? And these two are called what? Grating lobes, right? So why we have grating lobes? The grating lobes is usually because the pattern gets repeated, right? So the grating lobes likes the main lobes, and so to avoid the grating lobes, what we need to do is we need from the gamma, right? Set from this part. It equals lambda, right? Times cosine theta. It should smaller than 2 pi. Right? So over the visible region, so the theta varies, 2 pi. The theta varies from 0 to pi. Right? So that means what? So if we want to satisfy this equation, we need to set d smaller than how much? Lambda, alright? So smaller than lambda. So when d equals lambda, the gamma definitely equals to pi, and these two greater loads comes or exist. So that means d usually we set when we design the antenna arrays, when you set lambda smaller than and d smaller than lambda for that one, to avoid the greater loads. So this is a main consideration for us when we want to design the antenna arrays. And also, actually, when we for the designment, what we usually do is we set d as half of the lambda, right? To confirm that the greater loss disappears. And this is This is similar to the expressions for the Nyquist-Septin theorem, right? For this one. So this is the for the uniform distributions, and also another method to avoid the such applications, and also to reduce the side lobe levels. We introduced the binomial distribution. So that means the amplitude of the array elements, the AI, it cannot be a constant, all right, or equal to each other. It varies along the binomial coefficients proportional to that one. -1, dec, I, dec, right, and -I, -1, dec. Okay. So this is the expressions for that. And after that, we can do is reduce the side lobes and reduce the side lobes, but the beam width becomes wider, right? So it looks like this one. So this is the for the antenna arrays. After that, we introduce the electronic scanning of the arrays. Electronic scanning. So for this part, we applying a linear phase distribution. Right, so that means the psi node equals 0, psi 1 equals minus theta, psi I equals minus I theta, right? And so previously the delta is called the phase shift, right? Delta is related to a phase shift. And it can be expressed as same thing previously, cosine theta node, alright? Theta node is the scan angle. And then previously we set the expressions for gamma. Now set it related to gamma minus third. Alright, so gamma is kd or 2 pi d over lambda cosine theta minus kd cosine theta node. So it equals kd times cosine theta minus cosine theta node. So our expressions for example, for the array factor is related to f. Alright, our fa array factor is a function of gamma. Then it can switch to or change it to gamma prime. Just substitute this part by this part. Then we can get the expressions for the electronic scanning arrays. So then we introduced several kinds of antenna types, right? So for example, the Hall antennas, the rectangular antennas, and also the canonical antennas, right? So for the canonical horns, we obtained the so for canonical horns, generally it means the TE11 mode, right? So when we set, it looks like this one, and so the aperture diameter is d, and L, C is the slant length, right? So this length. And also the axial length, L node. So it has three parameters to represent the configuration of the canonical horns, and we note that for a fixed length of the x, for a fixed axial length, its directivity really use dc represented in dB, okay? And here is the aperture fold. So if we want to increase the antenna gain or the directivity, we need to increase the aperture d, alright? So this is d, or d or lambda. Then you can get that if L node is fixed, so then when we increase d, that means its directivity gonna increase, right? Increase, but it cannot increase infinite, and then it's gonna decrease. This one, and this is for L node, for example, 5 centimeter, for example, and if we want to increase the directivity further, so we're going to increase the axial length. So, for example, this one, L node equals 1. So that's why sometimes we wanted to see the for the high directivity antennas, its length is really very long, alright? And so further, simply L node equals 2, for example. And what we wanted to see is the maximum point, and we connect them together and get a straight line for that one. And so for the if we just consider the maximum directivity or the optimal point, so as if for a fixed slant length LC is fixed, what we can get is the as now we set is at the optimum point. So just this line, the equals the square root 3LC times lambda. So we can get the relationship between the exercise and the axial LC, the LC and the lambda, and then we can get the directivity. It equals 20 log of 10 by d over lambda minus 2.82. This is for optimal canonical Horn's expressions. 2.82. So, and for such a kind of Hall antennas, as physical actor and the relationship between the physical actor and the effective actor, it equals just 52% of that one, and so 2 times pi d squared. All right. So this is the calculations for the exercise and also the directivity of the canonical horns. And sometimes, if we just according to this rule and we want to design the antennas, or if the required directivity is too high, and we need to set the axial length or the slant length is very long, and maybe sometimes this under some limitations on the application scenarios, certain kind of antenna is difficult to fix or to use, and the method we can do is we use a lens couple. All right. So use a lens, then this can decrease the length of the antennas that we used, and so. But there is another thing that we need to consider for a lens-corrected Horn and canonical Horn is that because for free space radiation, the dielectric constant of the lens is really higher than the air, right? So there's some radiation is coupled into the lens and then radiated out, and there's also some is reflected, right? Because there's 2 layers of the interface between the air and the lens. So this gonna affect the amplitude and phase variations. This gonna lead to variations of amplitude and phase across that one. And then the wave impedance of the lens should be designed to keep the impedance matching between the air and the material. So, for example, we can cover the lens surface by a layer of material, like one. Then it can reduce the phase mismatching between the air and the lens. So this is for the canonical Horn antennas. So now what we want to do next is the slant antennas. Sorry, slot antennas. So for the slot antennas, here we just consider the rectangular slot antenna. So I think most of you maybe have seen about that, right? So we have a rectangular waveguide, example. Rectangular waveguide, and it usually is metallic waveguide. That one. Direction. Like this, right? So, and we have the slots cut in the walls of it. So the slots can be, for example, this is the longitudinal axis. And so the slots can be along this direction. It can also several kinds. Alright, it can be like this one, many kinds of directions. It can be like this, be like this also. So we have, it can be have several kinds of slots. So again, if let's plot it again. So if we wanted to design the or cut slots in the walls of such kind of waveguide, what we need to do first? First, we need to see the current distribution on the surface of this device. And not all of these kinds of the slots can be used for the radiation. It's determined by as dimension is going to affect the radiation, but mostly it's the position of it. It's going to be determined by it. So we plot it again. So if we have electric field input in this direction, and as current flow, or the surface current for the usually for the rectangular waveguide, and we just consider as the one node, right? So this is the basic of the dominant mode, really. And so as current, what is current gonna go? Like this one, right? This one, right? So this one, like this. And also this side, okay. And here's the current in this direction. So along this surface, it is usually parallel. Like that one. And at this side, it's gonna flows out like this one, right? If you can remember the directions. if you remember the expressions for the surface current in the electromagnetics. So you can see that along the longitudinal axis, the current is straight along this direction, right? On this side, the straight lines, even though their directions may be along that, opposite to that, but actually along the longitudinal axis. And on the surface side, wall. So they are usually parallel to the edges, right? So along these edges, and even though their direction is gonna change, but yeah. So how the radiation happens? So only when a slope only when a slope interrupts the flow of the surface currents. You can see interrupts. So what it means, interrupts? It means, for example, for this slot, it is perpendicular to this line, right? So that means it interrupts the surface current. For example, if we have a slot here along this direction, so it allows the current flow. So that means there will be no EMV radiated out from this slot. And also the same thing is for this slot, because it's also parallel to the surface current. So we can see that we can conclude that there's no interruptions. But all these other slots like this one, they will have the radiations out from the slot. So this is the condition for such a kind of the slot. And this is for the rectangular waveguide. Sometimes for example, the parallel plate waveguide, the things may be a little bit different because it has, for example, the slot extends from the middle of that to the end of it, and according to the simulations, it would have some kinds of radiations. And I would introduce publication on that during our presentation part, and I think maybe someone can choose that paper and for your presentation. So now what we want to do is the magnitude of the energy coupled by a slot. What it going to determine? By the slot. It's going to be determined by several kinds of factors, right? For example, the waveguide dimension, waveguide, and also the dimension of the slot, right? And also its orientation. And also another thing is if we set the slot at this direction, this position, or at this position, it's going to be different, right? The output, the coupled energy or the output radiation is going to be different because the current density for around this position or around this area is going to be different, right? So this means the density of the current or the surface current the slot interrupted. So mainly by such three factors. So if we want to consider a simple case, in such a case, we set a Cartesian coordinate system, and Cartesian coordinate system. So along this direction is the x-axis. We use a subscript A to represent just for the exercise of the straight guide, and this direction x, y-a. This is the y-axis, and on this direction is the theta a, the propagation direction of this guide, and so we set the aperture dimension of the input port, the dimension of the input port. This is A. This is B. Okay. So if we set a halfway, we just consider it as a halfway slot. For analysis. So what kind of a half-wave slot? So half-wave, that means one element should be half-wave. So B equals half of lambda. The A is much smaller than lambda. So for such a kind of rectangular waveguide, what is gonna behave? So it's gonna behave like, because it is much more smaller than lambda, it's gonna looks like such a small component. This is half wavelength, half-wave dipole, like this one. Do you remember the dipole, the Hertzian dipole? So its radiation pattern, like this one, right? This is side view of it, and from the top view of it, looks like this one, right? A circle. Top view, this is side view. This is the top view of it. So now what we consider is just if there is only one slot on the cut on the wall of this waveguide. And if usually what we want to do is we have several series of cuts, right? Or series of slots cut into the wall. So for an example, we have this one. So, this one, okay, and we have the slots, surface edge, parallels, this one, right, and then the green, this one. So it has several slots onto it. And what we need to do firstly, and according to our analysis on the antenna arrays, this is also a kind of array, right? So for each of it, there is also the mutual coupling, right? So for each kind, because now for each one, previously for the antenna arrays, for each element, it's going to radiate the radiation, and it's only determined by, for example, the fade, right? The fading part. But for such kind of a waveguide, all their sources is due to the coupling from the waveguide and coupling out from this component, right? So for the mutual coupling of the element between these elements or between neighboring usually elements, this is the main factor we need to consider, because it's going to affect or it's going to influence their radiation properties. Influence their radiation properties. And also gonna change input impedance, and also it's gonna cause reflection back to the source fading, and finally, at the end, what we want to get is the amplitude and the phase distribution, right? So this is the final it's gonna get. So what kind of the designs that gonna help us to reduce the mutual coupling? That means the distance between the neighboring elements D should be larger than lambda J. What is lambda J? Lambda J is the waveguide wavelength or the guide wavelength. It is different from the lambda, right? Lambda is the wavelength in free wavelength in free space. All right. So when the electromagnetic waves propagate it can propagate inside of the waveguide. That means it has a specific mode, right? So for such kind of specific mode or the dominant mode, or usually we set the lowest mode because we want to get the maximum energy propagation inside of the waveguide. So this is usually determined by the or it is related to the wavelength of the dominant mode. Or for the highest energy output is the lowest mode, the lowest order of the mode. So it can be expressed as, so for the lowest order mode, that means it's related to what? You know, the cutoff frequency, alright? Because for higher orders of the mode, it cannot propagate inside. So the lambda j can be expressed as certainly just for a rectangular waveguide, alright? So it's equals 1 minus c over lambda squared. So this is related to that. And from this expression, we can see that the lambda j, the guide wavelength, is usually larger than the wavelength in free space. Alright? So usually it's larger than h. Then when we come back to here, the separation of two neighboring components, it also has restrictions on it, right? So definitely, or roughly, it should be smaller than just a one wavelength in free space, right? So that means if we want to choose the separation d smaller than lambda, right? So to avoid grating lobes, and so when we consider these two conditions or the restrictions, it should be larger than lambda j to avoid the mutual coupling or reduce the mutual coupling, and it should be smaller than the free space wavelength to avoid the grating lobes. But actually, lambda j is larger than lambda, so certain kind of condition cannot be satisfied, right? Because it's larger than the lambda j, but it should be smaller than the lambda. So according to this condition, it cannot be satisfied. So then, what we can do? So for the mutual coupling, because why we set it, we usually want to set it is lambda j. So if we want to enrich or just exert the coupling, the mutual coupling, reduce that part, and the critical point is the distance d equals lambda j, right? So for d equals lambda j, that means there is a phase difference of how much? How much? 2 pi, alright? One wavelength corresponds to a phase difference of 2 pi. And if we want to consider these equations. So, for example, if we have two mutual elements, the one element is at this side, and another element is at this side, alright? Like this one. So it's for distributed at both sides of the longitudinal axis. So for this one and this one, and when we come back to look at the current distribution, we can see they have the opposite flow direction, alright? So for the opposite flow direction in the EM field, the phase shift is going to be how much? There will be a phase shift as how much? Pi. Alright? So pi corresponds to half of the guided wavelength. So that means our design for the D can be a half, can be only a half, and then it's gonna another half of the guided wavelength is contributed by the distribution of the elements, right? They are positioned on their cut at both sides of the longitudinal axis, and then you're gonna have a contribution of half of wavelength or the pi of a phase shift, and both together they can be a total one guide wavelength. This can help us to avoid the mutual coupling of that one. Okay, then let's take a short break. Continue later. 好，我们休息一下，然后继续。
我写什么地小样的？我之前也写了，小样的。现在又说小样的。我之前写的。还有它上面呢还有点也写的是哦，对。抑制那个奈菲斯特。奈菲斯特，可是一直它后老师就是小鱼，然后再就是为什么写稿？我不做贴写，我不做贴写，不贴写哪个？我要那个讲。我贴写也很重要。你做贴写真是挺不容易。不是。做贴写。还有一个做的更是。我不做贴写，我们只做频率。未来。我不做贴写。这个
So this is the considerations for the mutual coupling, and so we can set the distance between two neighboring elements to be half of the lambda j, and it contributes to a phase shift of pi, and then according to the current distribution, it contributes to another pi phase shift, and it relates to pi, right? And the coupling is perfect. And also, according to these equations, half of lambda j, it has the condition that it can be smaller, half of that, it can be smaller than wavelength in free space. So both conditions can be satisfied, and we can get, so for example, a perfect coupling, and also reduced the grating lobes. So this is a rough design for the slot antennas or slot antenna arrays on a rectangular waveguide. And also there is another condition that we needed to consider is for example, the longitudinal slot arrays. It can be divided into two kinds. So the design for that one is it is usually determined by whether it is broadside or whether its frequency coupling or this frequency radiation is changeable. So it has two kinds. The first kind is non-resonant array. So for the non-resonant array and resonant array also, whether it is resonant. Okay. So for the non-resonant array, that means for the resonant array, for example, that means for each element is in phase, so it's like the previous one. So for such condition is resonant array. So for such condition, if, for example, if the configuration or the structure of the waveguide and the slots are determined, that means its operating frequency is fixed. Alright, so we can call these two conditions. So the operating frequency is fixed, and because we want to get the in-phase array configuration, so this is the condition. And later for the non-resonant array, its operating frequency is usually much wider. It's going to be much wider. And so how it going to works? So firstly, for example, the symphony. We just show the front plane of the top plane of the rectangular waveguide. It has slots, rings, right? So as output, for example, we set a normal direction, this one, right? The normal direction, and the longitudinal axis, this direction, and the input side is here, this side. So if we have a variable frequency input, so what we're going to do is the antenna array, so the output angle corresponds to the plane as theta, for example. We define it like this one, and so the main lobe of the antenna arrays can be changed. So this theta cosine theta node equals lambda over lambda g minus lambda over 2b, the distance between two neighboring elements is d. So we can see that when the frequency changes, the output angle cosine theta node are going to be changed. So that means if we have variable frequency components input for 8 frequency components, it's going to have a different output angle theta node, and this gonna set it like a frequency divider. All right. So if we just set, for example, the side VLH, so this is, and we set the side, the main lobes, just use an arrow to represent it. So for each frequency component, we're gonna have a different output angle theta node 1, theta node 2, theta node 3, for example, 1, 2, 3, and they're gonna achieve like a frequency division. And for the for the TE1 node mode, the propagation of it in a rectangular waveguide is guided wavelength, and its wavelength in free space is related to a equals 1 over lambda over 2a squared. A as the width of the aperture. Width of the aperture, right? This is B, this is A. So this is the input, the non-resonant array, and also what it can be achieved by this one is because for certain kind of conditions, it's gonna have some reflections, right? So at the end of this part, we're gonna add, for example, a matched load. To what? A matched load. For what? For the impedance matching to reduce reflection. Alright? To reduce reflection. But if we add a kind of material inside of the waveguide, it also gonna lead to some absorption. Am I correct? So that means if we add the absorption, that means it's gonna lead it to less efficient than the resonant array. Alright, so for such kind of device or waveguide, it has many kinds of applications, right? For example, in the wireless communications, if we can set the output angle as frequency dependent or like a frequency division, it's gonna have several channels or links and output by just one device, and we can increase the coverage of the communication system. And this is the an application in other fields. And this is just the slot arrays. Microstrip antenna. So this is most commonly used, right? Especially for the mobile phones. And even though its efficiency is not that high, but it's easier for integration and low cost, and so it can be widely used for the small devices. So for a typical microstrip antenna, that means we have firstly we're gonna have a ground plane. So this is a ground plane. And on top of it should be a substrate. Alright, for any semiconductor devices, usually we need to put our structures and serial it onto a substrate, right? And so it is plane. This is a substrate, and on the substrate there is a microstrip, right? So microstrip. This is the microstrip. So this is the microstrip is usually a flat metallic patch, right? And it has its own, for example, its width, its length we use L, its width is W, and its height is H, for example. So, and this is just one view of H. And for example, the microstrip antenna, it has a fade, right? So the fade of it is where it comes. So let's take a side view of it. So actually, the ground plane like this. This is the ground plane. Okay, and under the ground plane is the substrate. So this is the substrate, and under the substrate is the metallic patch, right? The metallic patch, and if usually there is a coaxial feed line. feeder line. How it gonna works? So called axial feeder lines, and we change the color. So here is a here is also so this comes the feeding line and set the output from the telecommunications patch. Like this one. Usually it is along the known direction lines. Okay. And this is kind of the microstrip antenna with the coaxial feed line, and also there is other structures. So for such kind of direct structure, it has a structure like the feeding line, and this is maybe not convenient for our usage, and sometimes there is no such kind of feeding line past the road substrate. For example, anytime it has strip line, or microstrip line on the other side of it, and just for the feeding line like this one, it can also be used. And for such a kind of a structure, it's going to be much more integrated, right, and more convenient for usage. And the advantages, first we said that it can commonly used in many mobile phones, and because it's more because of its high integration, and the advantage of it is the power efficiency of it, right, or the power handling capacity. So the disadvantages. The first one is the low power handling efficiency. And also narrow bandwidth. So this is the disadvantages range. And when we look at how a structure can be when you want to use it, so it is for its length, width, and height. So for the length, it's usually between third of the free space to half of the free space, and the width is usually a quarter free space to the 3/4 free space, and h is around much smaller, it's around 0.003 lambda node, and smaller than maybe 1.5 lambda node. So this is the structure of the parameters. Restrictions on the dimensions of such kind of device. So, as we previously demonstrated, for just one element, it can have a broadside distribution, right? So, if we wanted to decrease the beam width and make the beam width is much more narrower, so we can have a series of patches, right? This direction, just like an array, right? So array, and for the design, according to our previous demonstrated, and they're gonna have a much narrower, right, beam width along the area, right? Just along this direction is big, it's narrow, but perpendicular to it is still broad side, right? So it's just like looks like a plane, or roughly like a plane. And if we want to let it to be a canonical beam, a narrow canonical beam, then we set it as the arrays again, right? The patches, several kinds of patches, microstrips, all of them micro patches, and just to sit onto the substrate and get a canonical beam. So this is the microstrip antennas, and previously when we firstly try to introduce the antennas, for example horns, rectangular, we say that the obey reciprocity. Could you remember this word? Reciprocity. So the reciprocity means the characteristics of an antenna The characteristics of the antenna is usually is what, such as the pattern, all right, or distribution, or impedance, all right, or the radiation pattern. Are the same, or the directivity, right? Directivity or the gain are the same when it is used at the transmitter side and receiver side. So if it has the transmitter side or the receiver side, it can have the same radiation pattern or directivity or the impedance. All right, this means the certain kind of antennas obeys the reciprocity. Actually, there should be some kinds of antennas. They do not obey the reciprocity, right? So if some obeys the reciprocity, that means there would be another kinds of the antennas. They do not obey such kind of reciprocity, and we call it active antennas. So for the active antennas, it is a class of antennas that contain active elements or the active electronic components. And so for the active antennas, it is different from our traditional antenna arrays. Active antennas, that means it also is antenna arrays, but its configuration is different from the conventional array. So for the conventional array, for example, we have 4 elements. We have 4 elements, and for each elements is connected to a phase shifter, right? And 2 by 2 together, for example. And it has a TR switch. And by the TR switch for the relay system, for the up converter or down converter, right? Down converter. So for the up converter, output usually follows by amplifier, alright? Usually followed by amplifier, and we have quite a high power amplifier. And for the receiver side, or for the receiver configuration, what we really do, there is also an amplifier, right? But at the receiver side, what we really used is a low noise amplifier. This is for a conventional. The conventional configuration or arrays, the phase shifter effect through divided phase and TR switch. So for the active array, it's still the same elements. We have 4 elements. So for each element, it has the O1 is fed by a dedicated transmit receiver module. So for H1, so this one is all of them, they share the same transmit receiver module, alright? But for the active arrays, for each element, they have the same transmit receiver modules. So for each element, the same thing. And also at the receiver side is the low noise amplifier, right? And the transmitter side is power amplifier, and also power amplifier, low noise amplifier, and at the end of it, we have all these then connected to a phase shifter. Then here the phase shifter is phase shifter. Add the phase shifter, and then we get them together and connected to AR switch, and for the up converter and down converter. Here we do not need the amplifier, the high power amplifier and the low noise amplifiers, because we distributed them into each element, like here. Alright? So we call this part is call this part to be transmitter, receiver, modules. So that's going to be TRM. And the array feeding lines is wrong. It's just this part. So for such a kind of the structure, because previously here, when we use the high power amplifier or the low noise amplifier, which determines the whole system. This kind of affects the. It gives us less flexibilities for each element, all right? For each element, because when this part maybe could not work very well, then it's gonna affect the whole system. But for this one, yes, it gives us more flexibilities, and of course for each element, they can control them by themselves. And another thing is that because for the high power amplifier, when we want to achieve the same total power amplification by adding up each element, the synchronization for each element should be a little bit different or difficult, right? Because each of them are separate or different. So this is the advantage for the active arrays. And actually, the another thing is to overcome such a kind of disadvantages for each of the TRM module. Each kind of modules, they can contain the, for example, the power conditioning and circulator and some other devices components, or the calibration circuit for each one to achieve that. So this is the active antennas or arrays, and so for the antennas, this is all about that we wanted to introduce, and of course I think we have some courses. This is more concentrated on the antennas, and I will not share more details about that. So after the antennas output, all right. So the electromagnetic waves gonna propagate in free space or in some medium, and then they're going to interact with our targets or our materials. That's going to be the next that we want to introduce, the interaction of the electromagnetic waves with our device, our materials that we want to use. So on our Earth, so the materials on the Earth can be classified into several kinds. The first kind is the homogeneous. Substrate or substance. Homogeneous substance and electrolytic solutions and also mixtures, all right? call it heterogeneous mixtures. The homogeneous substrate, for example, like pure water, right? Pure ice, right? And for example, the electrolytic solutions like the seawater, all right? It has salinity inside, all right? So, and for example, the source of the source or sugars dissolved in water, and the heterogeneous mixtures is going to be more commonly that we really used, right? Such like, for example, the sea ice or the ice is the mixture of, for example, ice crystals and also the liquid water or the liquid rings in chlorine. And what? For ice, it has ice crystals. Sometimes it has water in chlorines, and also what? For ice, they rarely has air pockets, right? And sometimes have airs inside. And snow is the same thing. The ice particles alright, exactly. And also air pockets or air. Air pockets, just air. And also some influences of like liquid water, especially for wet snow, right? And for the soil, also a mixture of soil particle. And for soil particles, they have many kinds of it. Alright, it can also be a mixture of it plus air. Alright, and sometimes for wet soil there is liquid water. Again. So for the homogeneous substance, it's convenient for us to analyze it because it has a fixed or a unique dielectric property for them, right? Even though it can vary or depend on the operating frequency. And for the electrolytic solution, because the substrate is one kind of material for the source, or the sugars, they dissolved in the water. And we can also regard them as a kind of homogeneous substance, and it has a unique or a combined dielectric constant or dielectric properties for that. But for the heterogeneous mixtures, because it usually has several kinds of different materials, they mixed with each other, and they do not dissolve inside, alright? So we can only regard them as one kind or several kind of inclusions distributed inside a host. So let's take an example. For example, for the soil. The soil, it has for example, for dry soils, there is no liquid water. Okay? There is just soil particles plus air. So if the volumetric distribution or the volumetric percentage of air is much larger than the is much smaller than the soil, much larger than the soil particles, then we can get air as being the host, and the soil particles can be enclosures. That means we have many soil particles. They are distributed, or they are inside a volume air, and then we can boast it to be a mixture. So for such kind of material or a mixture, how we can obtain there? Because we want to analyze the detection, sensing of some kind of material or an object. We need to know their dielectric properties, right? So its dielectric properties, or the dielectric constant epsilon. Here epsilon we can call it the mixture, the dielectric properties of this mixture. So it can be expressed as the dielectric constant of the whole media, and because, for example, if the particles, is not a circle, because it may be elliptical, or as short lines, that has their own orientations, right? For example, we have this one, an air cube, all right? So there is the soil particles inside of it, and the side is called maybe like ellipticals. They have their own orientations inside of it. So it's gonna lead to a fluctuation of it. So actually the dielectric constant is determined by the positions of the enclosures, alright? Also the orientation relative to the polarization of the electromagnetic waves, alright? So this is determined by this one. And here, this mean term, that means we just assume that it's not determined, it's distributed uniformly inside of this volume, and so it is not position dependent. And the fluctuations, definitely it is orientation dependent, also position dependent, like this term. So this is the average or mean value, the average term. So it equals the average of this part, average of it. And this is the fluctuation component. So that means, as mean value equals 0, right? Because it has many kinds of all of the randomly distributed, and so the mean of it is 0. So for this course, we would more concentrated on the average term. So for the average term, as we previously demonstrated, it is related to the real part and the imaginary part, right? And we're gonna continue about this part. Okay. Now we are gonna follow today's course, and we're gonna continue on Wednesday. Yeah. Okay. See you guys.哎，你好，你好，我刚下课，然后你送过来啊，可以，啊，可以，好的，啊，对，哎，好的，没问题，好，拜拜，差不多，对，
方向应该是对的。我准备以这个为基础找一些外部的。